So in the chapter number 3, we have gone through the one factor analysis of variance, where I call it as a treatment. You have how many levels of the treatments. Okay. Then I have shown you the technique is how do you perform the analysis of variance about the model itself. Okay, so that one is for the first week. I go through with you the chapter number 3. Okay, so for those students who are not familiar with the analysis of variance, at least you aware that how is it the working of the analysis of variance. Then you can break the components of the variant components to the difference of the component. So where we call as a sum or square. After that, we can compare the different levels of the means. Yeah. So after that, after the chapter number 3, I also go through with you what they call as blocking factors. So this blocking factor is considered as a Nelson factors. Okay, so you try to eliminate it out from the analysis. Okay, so this component of the blocking, you will try to break it out from the sum or square. Okay, so you try then after that you analyze your main factors. What is your study of interest? So the blocking factors can be the one blocking, or you can have a two blocking. So they have two blocking factors, then they use a Latin square. Okay, so these are all the instructions about here, where I wish to inform you what is meaning by the blocking. Okay, so after that, today we will go through another of this design is instead of the single factor, as you can learn from the chapter number 3 and chapter number 4, all these things is just a single factor. So from the single factor, we will extend it to the 2 or 3 or general factors. Okay, so where we call as a factorial analysis or the factorial experiment. Okay, so under the factorial experiment, I believe that I have started the introduction. Okay, so under the factorial experiment, you have what you can have is you have two factors, or you can have more factors. Okay, so for the two-factor analysis, we have a fixed effect. Under the chapter number 5 onward, we are concentrate only for the fixed effect model. Okay, and then we are using the analysis of variance to analyze the factorial design. Okay. Then this factorial design, instead of the two factors, we can extend the idea to the more than two factors. Okay, we can have 3 factors, 4 factors, and so on. Okay, so as your number of factors increases, then as you can observe that you have many different components in your model. Okay, then after that, in your factor can be the quantitative factor or the quality factors. Okay. So this thing will relate to the response curve and the surface. Okay, where you will learn it in the following. I think it's a few chapters. That one is for all the response surface methodology. Okay. So let us go through this example where I show you the diagram of the two factors first. What is meaning by the two factors? Then we can from this idea, we extend it to the two factors with more than 2 levels. Okay. So in this diagram, as you can see it out, we have a factor. A. Okay. In this diagram, we have a factor A. We have a factor B here. Okay, we have two factors here. So under these two factors here, we have a factor A and factor B. For each factor consists of the 2 levels. Okay, you only have a lower level and a higher high level. Here is a low level, we denote it as a negative. This one is a high level, I denote it as a positive. Similarly, for the factor B, we also have a low level and high level. We do not compare more than 3 levels and so on. Okay, for the illustration. Of course, later on, we can extend our idea to the 2 factors with many levels. Okay, So these are the values you can get, the values we obtain from the experiment. So if you observe it here, if you observe the diagram here, okay, so based on the first diagram, we will define it how the changes of the factor A and the factors B, okay, across the different levels of the, from the, for the factor A, the B is from the negative to the positive, means that the low level to the high level. For the factor A at the high level, B minus go to the B positive, means that the B at the low level go to the high level. So we can have a comparison of this thing, but this is a diagram given here, then we can plot the values here. If you observe this part, you can see that the factor A at the low level, okay, the B at the low level and the B at the high level, where the B at the high level is larger than the low level. Okay. Similarly, for the factor A at the high level, B negative is lower than the B positive. So after that, you get the two line will be parallel line here. Okay. So I will explain this one through the effect of here, or through the changes of the mean here. So if you want to look at the factor A alone, okay, you from the low level to the high level, is it the mean will increase? So from here, we just get the average value of the factor A. Average value of factor A is just these two values, average value, minus away the average value of the low level. So you can see that the factor A, as long as from the low level to the high level, they increase by 21 unit. Similarly, for the factor B. For the factor B, if you have a high level to the low level, you just take the average value of the high level here and the low level here across the factor B, then you can see that you also can have an increase in the 11 units here. So this one will show you that the factor A will increase from the low level to the high level. Similarly, for the factor B, they also increase. Okay, so this one is from the values here we can know. But more importantly, before that, we do not have the iteration factors in between the two factors, because what we have studied in the chapter 3 is only the single factor. Okay. In the chapter number 4, we also study the single factor, but we, instead of the single factor, we have another Nelson factors. But the Nelson factor and your factor of interest, they don't have any iteration at all. When we go to the chapter number 5, because we study the factorial analysis, so we have more than, we can have two factors or more than two factors. So if you have two factors, then we can have a factor A, we can have a factor B, we can have an iteration factor in between the A and B. Therefore, you can calculate the effect for the factor AB. What happened if they the changes of the AB? So for the case of the AB, we will take the average value of the changes of the cross product here, minus away the cross of here. Okay, then you will get the value is negative. Okay, so their iteration will be get the negative value of the effect. Okay. So this one is where you have these three factors instead of only the factor A and the factor B alone. Okay. So this diagram is show you that there are two lines of here. In fact, these two lines, if you draw it properly, their gradient may be not the same, even though from graphical here, because the iteration is a negative. Okay, your cross product here is negative. So this one is there is an iteration effect in between the A and B. Okay, but the value here is just a negative. It's not very large value. Okay.
Sorry, doctor.
Yeah. Can you hear me?
What does the negative one actually mean, the iteration?
The iteration effect itself means that one is increased and another one is decreased. Because you can see that you are referring these two, you're from the low level to here, and then you minus away. So therefore, one is increased, another one is decreased.
So if let's say the value is positive, that means that if one increase, the other one will increase as well, is it?
Yeah, yeah, because you can see that the value of the cross product here.
Oh, okay.
Yeah, okay. So after that, you can see from the second diagram here. you can observe here. Okay, this is another values we will put in here. Where for the case here is an iteration here. For the case here, you can see that it's a two parallel here, and then the iteration is very close to the look like it's no iteration at all. The effect here is -1. However, if you go to this diagram here, if you observe it, these are the experiment value you obtain. Okay, then we can see that the factor A will be from the low level to the high level, they will increase. However, for the factor B, you can get the negative. Means that you increase the level from the low level to the high level, they will decrease. Okay, then some more the iteration effect here. The iteration effect will be larger value. Okay, so this one is what they just show you the diagram of here. Okay. So if you show the diagram of these values, you can see that they consist of the crossing here. Okay, so this one will tell you that when we study the two-factor analysis, we need to consider the iteration effect there. But of course, the iteration effect may be very mild, it's a -1 here, or sometimes you will get the very negative, okay, or very positive value. Okay, so how large is it or how small is it? This one is we need to test the hypothesis. Then we only know that whether this effect is significant or not significant. The similar work is with the chapter number 3. You are testing the hypothesis, whether there is a significant difference in your means or no significant difference. Okay, we cannot just judge on the value itself. We say that there is a large difference. Okay, so this value is a large. If your value here is nearly 1,000, all this thing is nearly 1,000. The difference 29 may be considered as very small, relatively small. Okay, but if your value is around 50, 40, it's a 2-digit. This one also a 2-digit. Then we can consider as a large. But as I mentioned, how large is it? How small is it? We cannot be just doing the judging of the value itself. We need to further to the testing the hypothesis whether this iteration effect is significant or not significant. Okay. So this one is show you that there is an iteration, okay, where they have clearly there is. So sometimes the crossing is not very obvious. Okay. So the following one is about the factorial analysis. Because if let's say I have a two-factor, I would use the factorial analysis to do the analysis. Or I can redo the one factor at each time. I do the one factor at one time. The second thing is I do the another factor at the second time. So this one is one factor at a time. So if I do one factor at a time, means that the first time I do the analysis across here only. I will testing from the negative, for factor B from the negative to the positive. Then I want to know what is the changes. Okay, we stick it at the negative level. Okay. Another thing is we can be compare the factor A at here. We take it to the negative level. So we just compare one factor at the one time. So you will know that, okay, you're from the factor A from negative to the positive, what happened? For the factor B from negative to the positive, what happened? Okay, but you never take care about the iteration effect of these two cross product here. Okay, so this one is if we do it one times, then it's not very good. Okay, so this part is to show you that the what is of the factorial design to the one factor at a time experiment. Okay, so for the two factor case, okay, for the two factor case, the relative efficiency is factorial is 1.5 times more efficient than the one factor at a time. Okay, then for the three factor case, they have 2 times more efficient than that. Okay, so how they measure the relative efficiency, we need to look at is it they're comparing the variant or they're comparing other criteria. There is a criteria to do the comparison. Okay? So this one is show you that if you have many factors consider, if you do it one by one individually, then the one factor at a time is not as efficient as if you do the factorial analysis. Okay, so this one is mentioned to you that the advantage of using the factorial analysis. So in the factorial analysis, the presentation of the factorial analysis will be given by the following one. Okay, so you can observe that you have the first one is the first factor. After that, the second one will be the second factor. Okay, so from the factor A and factor B, this is a levels from the first level until the n levels. Just now I show you the example is only, for the factor A, only 2 levels. Okay, but in general, the factorial analysis can be extended to the A levels. Means that for the factor A, you consist of the many means. Similarly, factor B, you also consist of the many means. So this presentation is similar to the block. Let me see whether the block is here or not. It's similar to the block here. Okay, it's similar to the block here. But bear in mind that the block design, one of them is a block. This block is called the Nelson factor. It's not your interest of the study. Okay, but in the factorial design, both of them is your interest of the study, where we want to study 2 factors at the same time. So we have the factor B, we have a 1 level until the B levels. We have here. Okay. So after that, for each combination, for the factor A at the level 1 and the factor B at the level 1, we repeat it for the n times or the n replicates. So therefore, we have a 3 subscript, a 111, 112 until the 11n. N is referred to the number of the replication. Okay. So here I have mentioned to you A is A levels of factor A, B levels of factor B, and then the n replicates. Okay, so this one is called a completely randomized design. Okay. So after that, we need to know what is the model. Okay, because we study the factorial analysis, therefore this is a model you have. I believe that you have studied it before. The first one is the overall mean. The second one will be the tau I is referred to the factor A, or you want to refer it to the factor B also can, depends on what is your substrate of the I here. My I here is referred to 1 until A. So therefore, this one is the effect from the factor A. Similarly, for the second one, the beta J is the effect from the factor B. Therefore, my J is from 1 until B. Okay. After that, we also need to study about the iteration effect. Okay. The iteration in between the A and the B. So we can have here is what they have is a tau beta. So I will have a IJ. Okay. So this one and then plus the epsilon IJK. This one is considered as an error term. This error term is we assume that they follow the normal distribution with the constant mean and the they follow the normal distribution with the mean 0 and then the constant variant. Okay. So this one is a model here. Now we have an iteration effect here. Okay. So this is a linear regression model. In fact, it's a regression model. Okay. So the explanation you can get from here is a tau I is the effect of the I levels of the row factor A. This one is for the J level of the column factor B, and then this one is the iteration effect of the tau I and the beta J. And then here is the assumption of here the epsilon ij will follow the normal distribution with mean 0 and the sigma square. Okay, so here we are studying only the fixed effect model. We are studying the fixed effect model. So therefore, all tau I, beta J, and the tau ij, all these things is a fixed, even though the constant mean will be fixed. Okay. So from here, we will know that if you take the expectation of the yijk, okay, if you take the expectation is like the mean will be equal to the mu plus the tall I plus the okay. So this one is for your mean of here. Okay, because they take the expectation, and then because of here, you plus the expected of the epsilon ijk. Okay, this one the expectation is means that the mean of the under the epsilon here, the mean is equal to 0. So therefore, this part will equal to 0. Okay, we have a mean of the this thing, and then some more, we also have a variance of the yijk. Okay, so as I mentioned, we are studying the fixed effect model. So therefore, the mu here, of course, it's a mu, is an overall mean, is a constant. So we get the variance is 0 plus the tau I. This one is a fixed effect model, it's not the random effect model. So therefore, the variance also is 0 plus a 0 plus a 0 plus the variance of this thing, the variance of the variance for here is equal to sigma square. So therefore, you get the sigma square. Okay, so the mean for this model is given by here. Okay, where this last component will 0. Okay. After that, the variance for this component will be equal to the sigma square. Okay. And then because of the linear combination of here, epsilon ijk is follow the normal distribution. Therefore, we also will know that the yijk will also follow the normal distribution with your mean is given by this one. And then the variance is equal to sigma square. Okay, yij, because of the linear combination, this one is normal, then this one also will follow normal distribution. Okay, so this one is the distribution for the observation here. Because you assume that this thing follow the normal distribution, then this one also must we have here. Okay, and then furthermore, we study is a fixed effect model. When we study the fixed effect model, these are the constraints we have. The first one is a summation tau I equal to 0. Okay, the sum out of the effect, all the effect will equal to 0. The second one is a sum out for the beta j equal to 0. And then we sum out for the tau beta along the I from the 1 until the A levels, or along the B levels, they will also equal to 0. So these are the assumption is under the fixed effect model. Okay, I this thing out. Okay. So this one is a bear in mind that this one is a model, because this model will important when you calculate the residue. So for the factorial design, instead of writing out in the just now what we have before, I have a mu plus a tau I plus a beta j and the tau beta ij. We can group the whole thing together, is become their mean. Okay, we can be group them as a mean of the here, where the mu ij is given by the this one. Okay, so this thing is the other representation of the models only. Okay. So under the factorial design, we are interested is testing the hypothesis for the two-factor factorial design. We are interested to testing the tau 1 equal to tau 2 equal to tau A, then they equal to 0. If the tau equal to 0, because this tau present the treatment effect or the factor A effect. Okay, the factor A effect. As you can refer to this formula, if the tau I is equal to 0, the beta j also equal to 0, the tau beta also equal to 0. So this one is just a random error. The expectation of the mean will be equal to just a mu. So means that if all these things will equal to 0, the tau beta and the tau beta will equal to 0. So all the observations have a common mean. So if they have a common mean, it means that there are no difference in their mean. Okay. So therefore, when we testing the hypothesis, we will testing, if you want to testing for the factor A, we are testing that the null hypothesis and alternative hypothesis. It means that the tau I until the tau A is equal to 0, means that the treatment effect, all of them will equal to 0, or at least one of them is not equal to 0. If at least one of them not equal to 0, means that there is a difference in the different levels. Okay, so this one is for the factor A. Similarly, for the second one will be the factor B. This one is for the factor B. I use a notation as a beta. So if you have a beta 1 until the beta B equal to 0, okay, then at least one of the beta J not equal to 0. Okay. Then after that, if you want to testing for the iteration effect as well, you also will write down whether the iteration is significant or not significant. So therefore, you have a tau beta ij equal to 0 for all the combination of I and j, okay, under the H naught. After that, the H1 is at least one of the tau beta not equal to 0. But of course, we are not going to calculate one by one. We are using the idea of the analysis of variance, where you break the component of the variance, component of the sum or square to a few components. In this case, we already have a factor A, factor B, and the iteration of the AB. So therefore, we have a 3 component at least. Okay, plus another component is considered as an error. Okay, so instead of writing in this form, we also can be write it out as a H naught mean for the 1 equal to 2 mean for the A. Okay, for the all the mean are equal. So this one is say that the factor A different level, they don't have any difference. The H1, you will write it as at least okay, the H1 will be at least one pair of the mu I not equal to mu j. Of course, for the different combination of I and the j here. Okay, so the similar work also happen at here, the null hypothesis. You will have the mu1 equal until the equal to the mu b. Okay, then after that you have a H1 here. Okay, so this one is about the mean different level. Of course, this one we do not write as a mean 1 multiplied by mean 2. No. Okay, this one is just tell you that whether the iteration is significant or not. If the iteration is significant, then you are checking out how do you interpret the results. So this one is about the factorial design. You have a factor A, you have factor B, you have factors, the iteration factor of the A times B. Okay, so where the null hypothesis can be written in this form, or you can be written in the other form. Similarly, for this thing is over here. Okay. So the idea of the analysis of variance here, I just give you the some notation first before I break it to the different components. So if you still recall back what you have learned before, the yi double dot here, I use the first notation for the I level of the factor A. The dot j dot is stand for the j levels of the factor B. Ij dot is means that the total of all observation in the cell Ij cell. Okay, so because you have a Ij cell, the dot here is means that the total. Okay, we don't have the bar yet. The bar here, if you put the bar here, so it's mean. But if I just put the yi dot dot, means that the total under the levels, I level of the factor A. This one is a j level of factor B. This one is Ij, is means that the cell Ij. So yi that triple dot is stand for the overall grand total for all the observation. Okay, so this thing is I believe that you have tried the tutorial, you also can see it out. Okay, then of course in the mathematical form we have a summation of here. If the I dot is given double dot is given by you sum out for the I and the K here. Yeah, you sum it out for the sorry. Here it should be the not the I. Here I change it to the J for the B. Okay, you make the correction here. Okay. This one is for the I dot is you sum out the observation for the J and the K. From the K is 1 until N. The J is a 1 until the B. For the j dot is the sum out for the k and the I here. Okay. After that, you have the for the here the ij dot is just sum out for the k alone. So the mean was given by the y bar. Okay, the mean and the mean here. Okay, so these are the mathematical form for this thing. Later on, when we want to break the component of sum or square, we can break it using the following formula, and then we further can use this thing for the calculation. Okay, and then the following one, the y triple dot is actually the summation for overall, or the y triple dot bar, it will be given by the average value of here. Okay. So now we will go to the sum or square. If you still remember, your total sum or square will be equal to the observation minus the overall mean square. So this one is, I believe that when you go through the chapter 3, chapter 4, you can see that this thing is a general formula. So I call it as a sum or square for total. For any of the design, we just use the observation minus the grand mean square, you sum it out, then it's called the sum or square for total. Sum or square for total, right now, our model is consists of the Yij, okay, will equal to the mean plus the tau I plus the beta j plus the tau beta ij, okay, plus the epsilon ijk. Okay, our model is given by here. So therefore, right now we have here the sum or square for component is come from the tau, come from the beta, come from the tau beta, and then of course the last one is come from the error. So therefore, you have a first component. If you break it out, you have a first component is from the tau I. The second component is for the beta j. The third component is for the iteration of here. And then the last component, of course, is your residue. So this one, how to do it is, if you can refer back last time how I do it, I just add in the minus I dot dot plus the I dot dot, and then I do the expansion. So when you do the expansion, those of the iteration effect or those of them the cross product, they will cancel off. Okay. So this one will be noted as the first one will be the first one is SSA for the first one sum or square, SSB, SSAB, and the SSE. So the sum or square here will be given by this thing. Okay, but we get the sum or square is still not enough yet. Okay, because the sum or square may not help you to do any analysis. You need to know the distribution. What we are using the distribution is the F distribution. So F distribution is come from the ratio of two chi-square distribution, where each of the chi-square distribution divided by their degree of freedom. So sum or square, you still cannot be do the any type of the analysis yet. Okay. So if you observe, this is a formula for you to have the sum or square given by here. Okay. So here I also mentioned to you another statement here. For the last component in the equation 1, this is the last component what I mentioned here. Okay, for the last component in the equation 1, you must be at least 2 replicates to obtain the error sum or square. Okay, so if you only have a the only n equal to 1, then you can see that whether you have this component or not. Okay, so we have here. Okay. So this one is I show you the last component here. If you have here, this one is I, this one is J, the K is equal to 1 until if the N is 1. For the case is N equal to 1. Okay, so this one is if the case is N equal 1, the last component is 1. So you have a Yijk minus away the mean Ij dot square. Okay, Ij dot square. So here you can write it out as a summation of the I, summation of the J. So this one, the K is only for the Yij. Okay, the K is just a one observation minus away the mean of here. The mean Ij dot is means that you total out all the observation Ijk, divided by number of observation. So because it's only the last component, only one observation. Therefore, you have a yij1 divided by 1 only square. If the k is equal from 1 until the 2, therefore you get the average value of 2 observations. But if the n is equal to 1, I show you n equal to 1. So as you can see it out the formula. So this part will equal to 0. So therefore, in the analysis of in the factorial analysis, your n must be at least 2. If your n is equal, I show it to you, this part will equal to 0. Okay, so this one will go back to your case here. If the S is equal to 0, you cannot be perform the F test anymore. Okay, if the SSE is equal to 0, then you don't have the error to divide it. If you here can recall back what your F distribution in your single factor, in your chapter 3 or the chapter 4, you have a MS for the treatment divided by MS for the E. Okay, so if your MSE is equal to 0, where the SSE is 0, therefore you cannot analyze on the factor A, on the factor B, on the factor AB anymore because you do not have this component. Therefore, your N must be at least is 2 onward. Okay, so this one is a reason I have mentioned it to you. But of course, we can have other alternative. If let's say you still insist to have only N equal to 1, but we need to satisfy certain information. So that one I will show you in the following section. Okay, later later a few sections I will show it to you. Okay. So this one is here. I do not expect you to derive out this thing. Of course, if you're able to derive, it's fine. Okay. So this thing is actually I have write it out here. The expectation of the MSA. Okay. The expectation of MSA, where the MSA is actually the SSA divided by A minus 1. Okay. SSA divided by degree of freedom A minus 1, you will get your MSA. So if you take the expectation, they will equal to the sigma square plus the summation of the tau square divided by A minus 1. Okay, this is a formula for the expectation of the MSA, what you expect to get for the MSA. Similarly, for the expectation of the MSB will be given by the sigma square plus the AN summation of the beta J square divided by B minus 1. Okay, so because you study is a statistic, I cannot just give you the formula or you just use a R and then you just calculate, you get the final answer, do the analysis. Okay, so at least you need to know why the formula here, the formula, how did they do it? Because this one will prepare yourself if you want to know more detail about the formulation or in future you want to become the lecturer also. This all this background is important. Okay, we don't just apply it only. Okay? So the expectation of the MSA will be given by this one. The MSB will be given by here. Okay, because the MSA is you can see that the sum of square here is like the sum of square is a variant component. So they have a sigma square is here, where the second one is here. And then for the MSAB will be equal to sigma square plus this is a component. As you can observe that all of them have a similar pattern. Okay, so over here, beside this thing, also we can have a expected of the MSE is equal to SSE divided by their degree of freedom. Okay, so the expectation of the MSE will equal to the sigma square. So what is the importance of all these things? Because sometimes you want to know the sigma square. What is the sigma square? Sigma square is an error. I mean the variant from the model. Okay. You can see that this is a model we have. This is a component variant here. Because the variant here is important. This one is a true variant. Why I say true variant? Because this one is a true model. Later on, we can go to estimate the sigma square. So how are we going to estimate the sigma square? All this expectation will be tell you. the expectation here will be tell you if you use the expected value of the MSE will equal to sigma square. So therefore, if you're going to estimate your sigma square, you can be use a MSE. Okay. You use the MSE, then you can estimate the estimated of the sigma square is using the MSE to enter. Because you can show that the theoretically the expectation of the MSE, you simplify a formula, you can get the sigma square. Okay, so similarly for this part, if you want to get the this part of the component or this part of component, this part of component, then you can be using the MSA to estimate your sum of the tau beta square, your sum of the beta square, sum of the tau square. If you wish to have it, because the sigma square you can estimate using the MSE. But more importantly is the MSE here, because this sigma square is an estimation where they can help you to construct the confidence interval or testing the difference in between the two pairs. So you need the MSE, the sigma square here. So the estimated sigma square, we can use the MSE. Okay. So under the H naught is true, under the null hypothesis, then we will know that under the null hypothesis, then we know that the MSA divided by MSE will follow the F distribution. Okay, this part is similar to what I have mentioned to you. The first the F distribution will equal to the chi-square distribution for the first one divided by degree of freedom for the one over second chi-square distribution divided by their degree of freedom is 2. So for the 2 chi-square distribution, you will form the F distribution here. So the MSA is in fact is a chi-square over degree of freedom. Okay. So the MSA divide they follow the chi-square the F distribution with the alpha, and then the degree of freedom A minus 1 is referred to the degree of freedom for A. The AB n minus 1 is referred to the degree of freedom for error. So similarly for the MSB and the MSAB, also the same thing, where you have a B minus 1, here is a A minus 1, B minus 1, where the last one is a error for the degree of freedom for the error. Okay. So this one is how you're going to form your analysis of variance here. Okay. So once we have a F statistic here, then of course we can test whether the factor A, there is a significant difference, the factor B, and then the factor AB as well. So the ANOVA table for the two-factor factorial designs consists of the factor A, factor B, and then the iteration with the errors and the total. So as you can observe that the total is a total out from all this sum of square. Okay, and then their degree of freedom also not difficult to know. It's just if you have a A levels, then you have a A minus 1. Similarly, for the B levels, you have a B minus 1. If you have a AB, then it's A minus 1, B minus 1. Then after that, you get your mean square followed by the F statistic here. Okay. So based on the F statistic here, then we can compare with the we use the software, we can calculate out the P value. Okay, the probability. Then we will know that under the F distribution, what is the P value for each of the test statistic you have. Okay. So basically, the idea is come from the chapter number 3, decomposition of your sum of square, and then from the chapter number 4, then it followed by the chapter number 5. Okay. So for you to apply for the manual calculation, okay, the formula of the just now, the sum of square, we can be extended into the following form. If you can observe back just now what we have, the sum of square is consists of the here yijk minus the mean square. Okay, if you observed that previously the formula where I have shown it to you, they have a sum of square for these three. Okay. Okay, the sum of square will be equal here, but of course, when you do the perform the calculation, you can use the software or you can use the Excel where you key in your data, then you can simplify in the following form. It's just an observation itself, square minus the total square divided by total observation. So the sum of square for any of the design, they will consistently get the same formula for the sum of square for total. Whereas for the sum of square for the A, you are using the yi double dot square, means that you sum it out for the one particular of the level divided by total observation, you have sum it out. So if you have a sum it out for the Bn observation, then you divide it by Bn minus the grand total here. Okay, so the same thing for the B also, you are using the same formula. Okay, you can see the pattern of formula will be the same. Okay, however, for the sum of square for AB, for the sum of square for AB, you involve the two stages here. The first stage is means that you get the sum for the ij dot square, means that the sum for the each self square it out minus the grand total. This one is you get the sum of the square for the subtotal. You still not reach the AB yet. Okay, this one is a yij dot. It means that the cell of the ij. So you square it out. Then after that, you want to get the sum of square for AB is just equal to the sum of square for total minus the sum of square for A minus the sum of square for B. So this one is a shortcut for you to do the calculation for all the sum of square. Then finally, we no need to memorize the SSE. We just use the sum of square for total minus away the A minus away B and AB. Then you can get your sum of square for error. So if you do not want to calculate following way, then you need to, for the sum of square here, for the sum of square, yeah. If you don't want to calculate, then you need to using the following formula, means that the total for the one cell minus the total for the I level minus the total for the J level, and then plus the grand total square. So this one will be take a longer time where you need to sum out the I and the J observation. Okay. Whereas if you just consider the following one, you only need to simplify until the form of here. Okay. So for the tutorial one later, I also need to let you know. Okay. Somehow you can be use the computer software to do it, but as I mentioned to you, when we go through the test, we may I may not be just give you the table the values, okay, or you can use the software to do it. But certain question where I change the question pattern, even though I give you the data, you cannot be analyzed. Okay, I will explain it to you during the tutorial class. Okay, so therefore, for the sum table, certain of the table, I will given you the certain values. I ask you to fill in the blank for the rest of the table. Okay, the rest of the values in the table. Okay, so you need to able to know that the relationship of this thing, sum of square for total will be equal to the sum of square for the AB plus a E, you get the total. So all these things, I think that you can refer back. So now after this part, I will go through the first example, okay, for the factorial analysis. Okay, so we are studying the in this example, they want to design for the battery for use in a device that was subject to some extreme variation in the temperature. So the only design parameter that he can select at this point is the plate material for the battery, and he has 3 possible choices. Okay, so when the first one will be the plate, the material here. So when the device is manufactured and shipped to the field, the engineer is no control over the temperature extreme that the device will be encountered. And he know that from the experience, the temperature will probably affect the effective battery life. So therefore, in this case, however, the temperature can be controlled in the product development laboratory for the purpose of the test. Okay. So therefore, they consider only the 2 factors will be affected the life of the battery here. The first one is a 3-plate material. Okay. at the 3 levels of the temperature. Okay, so in this analysis, they want to know that what are the factor levels that will affect your battery life. The first one is, of course, the plate they use. Then the second one is a temperature they use. So it's a 15, 70, and a 125. So in this analysis, yeah, then of course we will consider as a represent the experiment in the following one. This one is a first cell. Okay, they run the experiment is under the material one, and then the temperature is a 15 Fahrenheit. Then you have these 4 experiments they run under this cell. Okay, so in this example here, of course, we don't have the Nelson factor. We don't have Nelson factor. It means that we can be assumed that all the materials is come from the same supplier. They don't have any difference if you use the different supplier raw material. Okay, so in this case, we do not have any Nelson factor. You have a Nelson factor later on. If you have a Nelson factor, then you just add in your model. Okay. So the experiment here is you have this one is for each one you repeat for 4 times. So of course I have a mention here. A I will denote it as a material type. B is I denoted as a temperature. Okay, so it's up to you. You can be denote the A as a temperature, B is a material type. So you can be change it. Okay. So what effects do the material type and temperature have on the life of the battery? So this one is the first thing. Is it you using the different material type they will affect the life of the battery in our time? Or you use a different temperature? Okay, is there any different temperature also? They can affect your life of the battery. So these are the 2 things will be affected your life of the battery. So is there any choice of material that we will give the long life regardless the temperature? So it means that is it when the temperature is changed, we don't care. When the choice of the material types, is it they were affected by the temperature? So this one is we want to see that whether there is any relationship of these 2. So therefore we study the interaction in between the factor of the A and the factor of the B. So based on these results, okay, here in this table, actually the circle here is represent the total. You total for the each cell of here. You total of here, and then you get the total of here. Then you will get the total for the sub of here, the total for sub of here, the total for here. Okay, so here are all the total, and then similarly for this one, the temperature at the 15 degrees Celsius this one is 1738 and so on, and then this one is the total for the each material type. Okay, and then finally this one is a grand total. So if you're using the analysis of this one is you can be use the R software. If you have a R software, then you can be do it using the software. Okay, as long as you key in the data in the different columns. Okay, the first column is referred to you have a temperature. You can be key in your material type is 1, 2, 3, and then your second column is your temperature 15, 70, and the 125, and then the third column will be your life of the battery. Okay, so therefore I will put in the AOV is in the R. We call the analysis of variance. Then they can perform for me. My data is called the battery data, and then here I will say that life is my data. For the life of the battery, the values will be I want to fit in the model is with the iteration. Therefore, I just write the iteration. They will know that we fit the model with the iteration. Okay, so therefore you can see that you have a temperature, your second one is a type, and the third one is the iteration, and the fourth one is your residue. Here they call as a residue. In fact, it's an error because different software they use a different name. Okay, so you need to aware that this residue is similar to what you have learned is a sum or square for the error for the SSE here. Okay. So the degree of freedom for each one, the material type, you have two levels, you have three levels, so therefore the degree of freedom 2. And then the second one is a type, the type also, you have a 2 of here. And then the temperature iterate with the type, you have a A minus 1, B minus 1, therefore it's a 2 times 2, you get the 4. So finally, you get your the residue degree of freedom. I also can't remember that what is the degree of freedom for residue, but you know that what is your total observation. In this case, you have 2, 4, 6, 6 times 1, 2, 3, 4, 5, 6. You all together, you have 36 observation. Okay, you have a 36 observation. Therefore, your sum or square for total, will be equal to this one is the total out. But the sum of square for total, the degree of freedom will be 35. So once you know these two, once you know these three, okay, 35 minus by 8, you will get your 27. So in fact, your residue one, you don't need to memorize the formula and the degree of freedom. As long as you know the standard one, the temperature or the factor A, factor B, factor AB, then once you calculate this thing and the sum of square, then automatically you can get the residue and then the sum of square for residue. Okay, because the different design of the analysis of variance, you can have a different formula for residue. But for the factor A, factor B, factor iteration, all these things is a quite similar pattern. Okay, as I mentioned here, you can see that the sum of square for A, T total, A, B, and the AB, they are in the similar pattern, even though you extend your model to the but the sum of square for error, you can have a different type of the formula. Depends on what is the model you have. Okay, so if you do it manually here, you don't go to calculate your sum of square for error. You will based on the sum of square for total. So after that, you get your mean square, and then you have a F statistic here. Okay, the F statistic here, obviously you already study about the this course, then definitely you know that this thing, the F value here is get it from the mean square from the temperature divided by mean square for the residue. So the here this value will be get it from the 19559 divided by 675. Okay, then you get 28 point something. 968. Similarly, for the second one and the third one, all will be divided by residue. Okay, just now I have shown it to you. MSA divided by MSE, MSB divided by MSE, MSAB divided by MSE. Okay, so all these three you have it. So on top of this thing, you after you get your F value, you also will know that this is called the P value. Okay, the P value here is means that if you refer to the first cell here, you have a probability of the F greater than 28. Sorry, hold on. You get this thing. Okay, for this thing is equal to the probability for the F greater than 28.968. Okay, so this one, the probability will be approximately 1.91 times 10 power of minus 7. Okay, so this one is a probability here. So this probability will useful when you're testing the hypothesis and then you compare with the type 1 error you set. Okay, then on top of here, they put the star here. It means that they are significant at the if they compare with the 0.001. If they compare with the 0.01, if they compare with the 0.05, then they give you the notation here, the double, triple dot, double dot, and one dot. Okay, so on top of this thing, you also will know that the sigma square, okay, the variance for the this model is equal to the MSE, where you can be get it out from the here is equal to 675. So the estimated variance of here will be equal to 675 here. So this variance here will be useful when you want to calculate, when you want to construct the confidence interval, then you may need the sigma square. Or you want to calculate the least the Fisher LSD and then the Tukey test, then you need the sigma square here. Okay, so this thing is what I mentioned is here when you go through this here. Yeah, here. When you're doing for this type of comparison, okay, then you may need the sigma square here. So in fact, you can see that they replace with the MSE. In fact, the MSE is their sigma square, but you do not know the sigma square. You use the MSE to estimate it. So therefore, you can see that this one is what I mentioned here. Okay. So this one is the estimation of here. Okay. So if you observe it, the ANOVA table is very simple. Okay, if you extend the idea, they can extension is they are similar. Their formula is quite similar. Okay. So from this analysis, what we can have a conclusion of here. The first one, we know that if we testing at the 10% level of the alpha, we know that this thing is a significant. So significant is means that the temperature, different temperature will give you the different, they will affect your life of the battery. The second thing, for the type here, also the p-value is quite small. So this one, the type, you using the different type, they will affect your life of the battery. The third one, the temperature and the type, the iteration, the p-value also were quite small. If we set your alpha at the 5% level, so you will reject the null hypothesis. So you reject the null hypothesis, it means that the iteration effect will be affected your results. Okay. So this one is this one is a result you get from the ANOVA, the R. Okay. So of course we can be plot the mean. I just plot the mean for you. You can observe it. If you from the temperature 15, 70, and 125, you can see that average life will be dropped. Okay, the mean will be dropped. But from here, we only know that they are dropping, but we do not know whether there is a significant difference in between the this one, the 15 and the 70, or 70 and 125, or 15 with the 125. We do not know have a difference or not. But just now, based on the analysis here, we know that there is a significant difference. Okay, but we do not know which specific pair there is a significant difference. Okay. So similarly, for the type of the material, if you're using the first type and second type and the third, you can see that the average life will increasing. But we also do not know that whether the type 2 and type 3, there is a significant difference or not. Okay, but we know that based on the result here, we know that overall, if you're using the different type, of course, there is a significant difference. But we just do not know which specific pair there is a significant difference. Okay. So therefore, after that, we need to run the what they call as a Tukey test and then the LSD test to test which specific pair will have a difference. Okay. So now we go to plot. Another thing is this plot is called the iteration plot here. Okay, because just now based on the result, we show that the iteration is significant. What I say significant is means that they have a different. Okay, significant is means that they different. Okay, so if I plot the plot here, as you observe it here, this one is a degree for the 50, 70, and the 125, and then this one is the average life here. So the color, different color is represent you are using the different type. Okay, so as you observe here, there is a crossing here. Therefore, you can see that you have the iteration is significant. Okay. Then from this one is only the two factors we can be illustrate using the graphical way to represent our results here. Okay. So if you observe that when the iteration is significant, okay, what I say the iteration is significant is means that this one, This one is what I call as an iteration effect here. The temperature and the type here. When the iteration is significant, then we cannot be analyzed or we cannot give the conclusion on the temperature alone or the type alone. We need to take care about the iteration effect here. Unless the iteration is not significant, means that is no different for the iteration, then when you interpret your result of the temperature, you can be interpret it separately, and then the type of the material also you can interpret it separately. Okay, but because of this, in this example, the iteration is significant. Means that if I set the alpha at the 5%, so the alpha will be larger than the p-value. Then you have to reject the null hypothesis. You reject the null hypothesis, it means that the iteration is significant. Okay. So from this one, as you can see the plot here, this one is a code if you want to draw the R code. Okay. So as you can observe it here, if the iteration is significant, when you're talking about here, at the 50, temperature at the 50, 15. If you use the temperature at the 15, which one will give you the highest average life? If you need to use a material type number 2, so they will give you the higher life. Whereas if you are go for the 70 degree, then you should be choose the highest one is you need to choose the type 3. Then for the last one, 125, you still choose the type 3. So this one is tell you that the iteration is how important the iteration. Because if you set your temperature at 15 degree, you cannot be use a type 3. Okay, so you need to use the type 2 as your material so that you get the average high life. The average life of the battery is high. Okay. So this one is about the iteration plot here. Okay. And then here, as you can observe it here, this one is the table for the three material type at the 70 degree. So we only concentrate on the 70 degree here. Okay, if we concentrate on 70 degree here, then we only concentrate on these 3. If we want to use, of course, we want to use the highest one, you use the number 3. But number 2, we still can be used because we need to check whether there is a significant difference in between these 2 or not. Okay. So I will concentrate on the 70 degree. Of course, you can concentrate on the 150, 125, and you can concentrate on the 15. Okay. So the first one is here. We concentrate on the 70 degree. Here you have the mean for the first one will be 57. The mean for the second type will be the 119, and then the mean for the third type will be 145. So we have here because we know that the material type there is the different. So is there any difference in between the 2 and the 3? But of course, the 57 and the 119 is quite different a lot. And then similarly for the 57 and 145 also quite different a lot. But these 2 is what we are interested is whether these 2 is close enough or no need or they are different. So I have in the chapter 3, I have shown it to you. There are 2 techniques of them. One is based on the Tukey. One is based on the Fisher LSD. Of course, you can have other techniques. Okay. So if we want to base on the Tukey techniques, then we need to find the Q from the Tukey table. Okay. So this Q here, actually just now I have uploaded the tables. Okay. This is a statistical table. You may need it. Okay. The statistical table here I have uploaded to the spectrum. Okay, so you have many of the different table. This one is a table for T distribution. Then this one is a table for chi-square distribution. This one is a table for the F distribution. And then for the just now I mentioned is here. The Tukey test one is here. If you have a textbook, also you can get it. This one is for the Q for the Tukey, the critical value. Okay. So sometimes the software, even though you use R, they don't have the any of the ready software. So in that case, you need to know the formula so that you can do the formulation. Okay. So we go back to here. So this Q value, I will get it from the Tukey table just now, this table. Okay, with the degree of, with the first one is a P, and then the second one is a F here. Okay. So you, after that, you square root the MSE divided by N here. So this one is a critical value. The 45.47 is a critical value. So therefore, you find the difference in between the pair number 1 and the 3. Then after that, you compare with you find the 3 and the 2, and then the 2 and the 1 here. You can see that if you get the difference here is 88. The difference of the means is 88, and then 26 and 62. So obviously, this one, the pair number 1 and 3, they greater than the critical value. So we consider they are significant different. Then after that, you have a 2 and the 1, also they greater than this thing, is considered there is a significant difference. So you can see that if you observe this thing, if you observe this one, the mean here, you have first mean, you have a 1, 2, you have a second one is 2, 2, you have a third one is a 3, 2. Okay, so you have a 3 mean here, I order it here. So we can see that the 1 and the 3 here, there is a significant difference because you can see 1 and 57, they're quite huge different. Okay, and then another one will be the pair of the 2 and the 1 here. The 2 and the 1 here, these two also they are significant different. Okay, the only no difference is a 3 and the 2. So means that even though you can see the value here is 119 and 145, but in fact the test it show you that they are not significant different of these two material. So means that at the 70 degree, at the 70 degree of this temperature, we can be use the material 2 or material 3 because the result is show you that is no significant difference for the 3 and the 2. So this result is only applicable for the 70, the temperature at the 70. Okay. So if you you test the different temperature, let's say you're using the temperature at the 15, then you may get the different result. Similarly, if you use a 125, you also may get the different result. Okay. This one is to show you that when you have an iteration effect, you cannot be test in general for the changes of the this thing, okay? Or you want to changes of the different type of material. You need to fix the certain level of the temperature or the material type, then you do the comparison. For example of here, if I fix at the 70 degree, then after that I compare for the 3 material. I fix at the 125 and compare with 3 material. You also can do that is you fix at the material type 1, then you compare with the different temperature. You fix at the material type 2, then you compare with their different temperature. Okay, so this one is when you have an iteration effect is significant. Okay. So this one is what you can be recall back your chapter number 3 here. And then this one is a result is here. So the analysis is indicate that the temperature at 70, battery life is the same for the material type and 2 and the 3. And the material life for the 1 is significantly lower in comparison to the both 2 and the 3. Okay. So this one is what we can compare here. So of course, based on these results, if you cannot find the material 3 to be used, then you can be replaced with the material number 2. Because based on the analysis here to show you that they are not significant different. But of course, they fix it at the 70, the degree of the 70 degree. Okay. So this one is one of the example to show you that how important it if you have the iteration effect is there. Okay. So we just continue one or two more slide here. So when after you know the model itself, of course, you also need to know what is the model estimated parameter. So to estimate your model consists of a few of the components. The first one is the overall mean. The second one is a treatment effect for the I. The second one is a beta J. And then the third one is an iteration. Okay. So to estimate the overall mean, we were using the overall mean of the data set from the data set to estimate the overall mean. Similarly, if I want to estimate for the tall I will use the observation, the mean for the I treatments minus the overall mean. And then the beta J will be the mean from the J unit minus the overall mean. And then the iteration will be here. Why you need to get all these things? Because all these components were related to your model. Okay, once your model you have, then you can find out the fitted equation. So the fitted equation here, I will have a use the notation Yijk. I use a hat here, it's called the fitted equation, will be equal to the mu hat plus the tall I hat plus the beta J hat plus the tall beta Ij. Okay, when you have a fitted equation, of course your error term is don't have anymore. Okay, so this one is a fitted equation. So the fitted equation here, you will replace this thing with the mean here. Then plus the, of course, the second component will be the equal to the mean. Okay. Plus the third, plus the following component. Okay, and then plus the last component here. Okay, so this one is called the fitted equation. Okay, so as you observe it, maybe I write it not very clear. Later on, I will change it. Then I will rewrite it out again. Okay, if you can cancel off all the component, because here is a minus, here is plus and plus here. So all this grand total will can cancel off. You have a ij, you have ij here. You can cancel off it all. So finally, you get your fitted equation. It's just the fitted equation here. Okay, you get the fitted equation will be equal to just the component of the y. The fitted equation is only you have the first one is here only. Okay, for this component. Okay. The fitted equation, as you can see out all these things you can cut off. You only have an average value from the each cell. It become your fitted equation. Okay, so therefore when you calculate your residue will be given as a notation as a Eijk. Okay, because you have a 3 subscript will be equal to the observation minus the fitted equation. Okay, so the residue will be equal to the Yijk minus the fitted equation will be equal to just the Yij dot. Okay, so this one is your refer to your residue. Okay, so you need to check your residue is because you want to check the assumption of the normality, constant variant, independent. So therefore you use the residue to check, because this residue you get from the data set. Okay, then you can be checked whether they fulfill the condition or not. If they do not fulfill the condition, of course you can do the transformation of the data. Then your analysis of variant just now, you only can get the valid analysis of variant table. Okay, so this one is just double checking. Even though you fitting for any model also, we need to back test back whether this model they fulfill the assumption where you set it before. Okay, so I think I will stop until here. Okay, I will stop at this stage. Then we go for you go for the break of those of the Muslim, they may need to go for the prayer. Okay, then we continue back at the 8 o'clock. Then today we have another section, it's a tutorial section. Okay, then I will explain more about the tutorial question because I only supply you the solution. I have supplied you the solution, but the working through the handwritten or the manual working, I think that some of you may be not clear about it. I will explain to you. Okay. Okay.